The next couple of examples are looking at homogeneous first order ODEs. This term homogeneous means something differently than what it meant before, and something different than it's going to mean in the next chapter that we cover. But homogeneous, as far as a homogeneous first order ODE, means that you can substitute Tx in for x and Ty in for y into an ODE and then be able to factor out t to some power times f of xy. If you do have a homogeneous ODE, then you can make a substitution, either u is equal to y over x or v equals x over y. Oops, sorry. Come back. The most common substitution is the second one, v equals x over y, and then it will change the homogeneous ODE into one that's separable. So let's look at the first example, which is number 4. Determine whether this is a homogeneous ODE, and if it is, then solve the equation. Notice that here on the right side of the equation I have my function of x and y. So f of xy is equal to the right side, is equal to y squared plus 2xy over x squared. To show that this is homogeneous, you'd want to substitute tx in for x and ty in for y, and then be able to factor out t to some power. And so this first term here, y squared, would become ty squared. And then on my second term, 2xy, I'd have 2 times tx times ty. In the denominator, my x squared becomes tx squared. And then simplifying this, I'm going to get t squared y squared plus 2, and here we get t times t, that gives you a t squared, and then x times y. In the denominator, tx squared gives you t squared x squared. And then notice that you have the t squared in common in the numerator. You could factor the t squared out to give you y squared plus 2xy. And in the denominator, you also have that t squared. And so you can cancel out these t squareds. And if you wanted to, you could write this as t to the 0 power times y squared plus 2xy over x squared, which is y squared plus 2xy over x squared, gives you your function, t to the 0 times f xy. So this is homogeneous because you can factor those t's out, and is homogeneous order 0. Okay, because it's homogeneous, we can make a substitution. And the substitution that we're going to make, we could either let u equal y over x or v equal x over y. Now let's see what our equation looks like. Here, because we've got y's over x's, we would want to let u equal y over x. Notice that if you wanted to, you could rewrite this fraction so that you have y squared over x squared. I'm going to write that as y over x squared, that's an x, plus 2xy over x squared. Here I can cancel one of the x's, so I have 2 times y over x. So notice that these y over x's will be substituted in, and they'll just become u's. You're going to have u squared plus 2u. When we substitute in, we also want to substitute in for dy dx. So let me go ahead here and solve for y. Y is x times u. So dy dx. On the right side here, you want to use the product rule. The derivative of x with respect to x is 1. So I get 1 times u plus x times the derivative of u with respect to x, du dx. Okay, so when I substitute in place of dy dx, I'm going to put u plus x du dx. That's my dy dx here. Is u plus x du dx is equal to the right side of the equation, which is y over x squared. Y over x is my u. So I get u squared plus 2 y over x. And again, y over x is u. This is my new equation after making the substitutions. And we can start by subtracting u from both sides of the equation to give us x du dx equals u squared plus u. And notice that this is separable. If I want to bring my x terms to the right side of the equation and my u terms to the left side, I'll have to multiply by dx over x, and I'll have to divide by this u squared plus u. So that on the left side the x's and the dx's cancel, and I'm left with 1 over, let me write this in factored form, u times u plus 1 du. That's my u squared plus u factors into u times u plus 1. On the right side, the u squared plus u cancels, and you're left with 1 over x dx. From here, you want to integrate both sides. On this first integration, you want to use partial fractions. I can do that off to the side. If I have 1 over u times u plus 1, that's equal to some number divided by u plus another number divided by u plus 1. If you multiply this entire equation by the common denominator, u times u plus 1, then you get 1 on the left side of the equation because the u and the u plus 1 cancels. On the right side of the equation, on this a, the u will cancel to leave you with a times u plus 1. And here for the b term, the u plus 1 will cancel, and it leaves you with b times u. So simplifying the right side of the equation, we get a u plus bu. That's my u terms. And then plus a is my constant term, is equal to 1. You want to set your constants equal to each other. That tells you that a is equal to 1. And then the u terms should also be equal to each other. Now there's not a u term on the left side. If you put a u term there, the coefficient is 0. That tells you that 0 is equal to, my u term on the right side has coefficients of a plus b. A is 1. And so subtracting 1 from both sides, we get b is equal to -1. So b is -1, a is 1. And I can write this first integral as 1 over u, and the second integral as -1 over u plus 1 du. And then on the right side I have 1 over x dx. Well, when you do the integral of each one of these fractions, you're going to end up with natural logs. I'm going to change my ink color because this is getting crowded so that you can follow the progress. I'll come up here and do my integrals. The integral of 1 over u is the natural log of u minus the integral of 1 over u plus 1 gives you the natural log of u plus 1. On the right side of the equation, the integral of 1 over x is the natural log of x. And then I have my constant of integration. I'm going to bring all my log terms over to the same side of the equation. So let me bring that natural log x over. So I have natural log of u minus natural log of u plus 1 minus natural log of x is equal to c. And then combining these natural logs together, we're going to get natural log of u divided by u plus 1 times x. That x comes down in the denominator also because of the negative coefficient, is equal to c. I'm going to apply the exponential function in order to cancel out that natural log. E and natural log are inverses of each other. It's going to give you u times, or u divided by u plus 1 times x equals e to the c. I'm going to multiply by the common denominator. So that's going to bring my u times u plus 1 times x up. I get e to the c x times u plus 1. Well, and at some point I need to substitute back in for u. I was going to write out for u, but let me substitute now. We know that u is equal to y over x. So wherever I have my u, I'm going to place y over x. And I also want to simplify this a little bit. I'm going to make a replacement for this e to the c power. I'm going to let k equal e to the c, so that this becomes y over x equals kx times y over x plus 1. My goal is to see if I can solve for y. And so I'm going to start by multiplying through by x to get rid of this x in the denominator. That's going to give me an x squared here. It'll leave me with the y by itself on the left side. And then when I distribute through by the kx squared, I'm going to get kxy, one of these x's will cancel, plus kx squared. I want to bring my y terms together to one side of the equation. And when I do that, I'm going to factor out the y. When I bring this kxy over, it's going to become a negative. And then divide both sides by 1 minus kx. And we have our solution to the equation.